non-symmetric symmetries, which, as you see, is the background of this physics. And then on to topological semimetals, and then how you can actually use non-symmetric symmetries to induce nodal-line semimetals by vacancy engineering crystals. And I'll show you that this works at least in 2 case studies that we have carried out for graphene and borofene. And then I will move on to talk about the non-interacting case vacancy-engineered graphene and some key results for this material, which are relevant for studying the weakly, strongly, and intermediately interacting regimes of these materials and how these interactions can drive a phase transition. So, okay, about non-symmetric symmetries, in 2 dimensions, which is the number of spatial dimensions these materials live in, we have just 17 crystallographic groups, which are called wallpaper groups, and they are represented by this nice wallpaper types of patterns. And of course, they are classified according to their symmetries. And among these 17 groups, there are only 4 non-symmetric groups. And in 2 dimensions, there's just one symmetric operation, which is called the glide line, which means that the symmetry involves a mirror, a reflection, but a translation of a fraction of the unit cell in your crystal. And there are these 4 non-symmetric wallpaper groups. And just a little joke that 3 years ago, when I started looking into this kind of, into materials that are non-symmetric in 2D, my then 10-year-old son, Francisco, when somebody asked me, what kind of materials do you work with? He said, she works with tiles. Because for him, that's, you know, seeing these pictures that he connected with tiling and this kind of patterns. And in fact, it is about tiles, but just in a quantum scale. So, okay, topological semimetals generically come in 3 flavors: the Dirac semimetal, Weyl semimetals, as we talked about before. They typically come, they have to come in a way that the valence and conduction bands, they touch in 2 points, as opposed to a Dirac semimetal, you have just one touching or crossing point. Typically, the dispersion is linear around this band touching or crossing points. And then you have these nodal-line semimetals, where these bands, they cross or touch along lines in the Brillouin zone. And I'll be focusing on this type of material, nodal-line semimetals. They come with their own novel topological classification. Arguably, they are good hosts for superconductivity, magnetism, and a zoo of strongly correlated phases to develop. And I will be focusing on the case of unconventional magnetism that can arise in these materials. So, okay, generically, band degeneracy, not just nodal lines, but band degeneracies in general, when they are subject to perturbations, one of the 2 things can happen. They can, perturbations will either open a gap and destroy the degeneracy, in which case this degeneracy is called accidental. This typically happens in the presence of symmetric symmetries, which do not involve a fractional translation of the unit cell, and very often combined with spatial inversion, or with time reversal symmetry, or chiral or particle hole. There are non-spatial symmetries, or this degeneracy is robust against perturbations, in which case they are symmetry enforced, and this happens in the presence of non-symmetric symmetries. And for a topological classification of this kind of band degeneracies, very comprehensive classification, I'm citing here this very important paper. But moving on to the idea of this talk. So if you want to have a nodal-line semimetal in which this nodal line is symmetry enforced, so you can just go and find a non-symmetric material. And this will be basically typically found in the three-dimensional crystallographic groups. And that involves searching through a large class of materials, and which are three-dimensionally. Typically, they are not monoatomic and hard to integrate with quantum technologies. What we are offering here is to design a 2D non-symmetric monoatomic material by vacancy engineering, or poking holes in your two-dimensional, otherwise symmetric lattice. And this should be compatible with a range of quantum technologies and semiconductor technologies and so on. And I give here a set of papers where we explored this idea. So this work was done in collaborations with, unfortunately, Professor Fanuai, who used to be my colleague at University of Brasília, passed away recently, but he was part of the initial works. And Professor Igor Zutish from Buffalo, Wei Chen from PUC-Rio, and at that time, the PhD students, the respective PhD students. So let's look at borofin or graphene in their pristine crystal structure. So they both have two orthogonal reflection planes, which ultimately give rise to this Dirac cone, which under perturbations will be gapped. So here, the idea is to remove some of the borofin or graphene atoms in a periodic way, not remove, the material has to be grown in such a way. But so these vacancies will basically remove one of the reflection planes and exchange it for a glide plane, which is a non-symmetric symmetry. And as a result, very briefly, you gain a nodal-line, which is robust under perturbations. And if you want to understand how this comes about from a fundamental level, you can just recognize that a lattice like this can be mapped into a minimal lattice, that the basic structure is that you have a 4-site unit cell where you have this mismatch between the points in the unit, the sites in the unit cell. And then if you just write down a 4x4 Hamiltonian for this toy model, and you impose the glide plane invariance relation, which writes down like this, you see that this glide plane transformation will change one of the momentum, will flip one of the momentum coordinates, and basically there will thus be invariant glide plane eigenspace when this ky, in this case, is either 0 or plus minus pi, which means that in this glide invariant space, this operator commutes with the Hamiltonian, and therefore the Hamiltonian eigenstates are also eigenstates of this glide operator. In this case, this will be the eigenvalues. And we can construct this operator for that particular toy model, and it will be like this. And in this case, the eigenvalues of this operator are just this number, these complex numbers. And the point here is that these eigenvalues, skx, because they now depend only on kx, because ky is fixed. So as skx is run from minus pi to pi in the Brillouin zone, these eigenvalues will circle in the complex plane like this, right? And the point is that this eigenstates here, they are degenerate for the glide plane eigenvalues at these points. And what this means for the eigenenergies of the Hamiltonian, which commutes with the glide plane operator, is that the swap of the eigensectors from minus pi to pi necessarily means that these four bands have to cross somewhere, anywhere, along this kx direction. So because this state becomes this one, and this state will have to become this one, according to this degeneracy here, the energies will have to cross somewhere along the kx direction. So this band degeneracy is unavoidable. It's very different from vial nodes, for example, that eventually will split up if you introduce a strong enough perturbation, because although topologically protected, they are accidental degeneracies. Here, no, these degeneracies are symmetry enforced. So no matter how strong the perturbation, if it doesn't break the symmetry, these points can move along kx, but they cannot, a gap cannot be opened at this, between those bands. Okay, so you can also, another way to see that is you really go and write down a tight binding Hamiltonian that contains, say, just hopping between next nearer neighbors, and this 4x4 matrix will have some generic elements that will look generically like this, and you just go and impose the glide plane, the glide symmetry, and in that case, we have also inversion symmetry, and the invariance relation just looks like this. And in that case of the toy model, we also have time reversal symmetry, which in this case writes down like this. And you just plug everything in, because you can write the respective matrices for each one of these transformations. You plug everything in to this three invariance relations, and you extract the constraints on the entries of the matrices, and you just can do this diagonalization with Mathematica, and you see that if you go step by step, first you impose glide symmetry, and you do get this, that these four bands will necessarily touch at, in this case, 2 points along kx, 1 point for one pair of bands, and another point for the other pair of bands. And for ky equals 0 or pi or minus pi. And if you progressively include the second symmetry, which I told you is inversion, what it does, it just pushes those 2 points to kx equals pi, and then time reversal symmetry will join those symmetry enforced points along parallel to the ky direction. Accidentally, it also generates an accidental nodal line at ky equals 0 when you impose time reversal symmetry, but that's not very important for today's talk. Which is also not important for today's talk is that when you introduce anisotropy, this line, which is accidental, can actually move because it's not symmetry constrained to be in a high symmetry locus in your Brillouin zone. So it can actually move inside the Brillouin zone, and eventually it will be gapped out if your anisotropy is too strong. But so we test this idea for real materials, so borophene, 2 types of, actually tested for more, but let me show just two examples. So we do get this symmetry enforced nodal lines where they should be, and also these nice accidental nodal lines inside the Brillouin zone. And when we introduce spin-orbit coupling, with a very large value for spin-orbit coupling for this type of light atoms, but just for the sake of argument, we see that despite the accidental nodal lines being split because of spin-orbit coupling, and eventually they will be gapped out, these symmetry-enforced nodal lines at the edges of the Brillouin zone cannot be removed at all. We tested this also for carbon, for graphene, and we get the same results, okay? So in this case, the symmetry-enforced nodal lines will be in this direction because the glide plane is in this x direction. And also we get these accidental nodal lines which are induced by anisotropy inside the Brillouin zone. They are very robust, although they are accidental. Okay, so now moving on to the second part of my talk. We know that pristine graphene, when you introduce electron-electron interactions in pristine graphene, it becomes a magnetic insulator for sufficiently large electron-electron interaction. And this is the result that's well known from the literature. It's around 3.8, the critical value of U, which is the strength of electron-electron interactions. for the critical strengths for electron interactions in pristine graphene. So the question here is that what happens with this scenario when you remove some of the carbon atoms of graphene in a way that it becomes a non-symmetric nodal-line semimetal? And that's the question that we set ourselves to answer. So these are the collaborators in this part of the work. Professor Teresa Paiva from UFRJ. Andressa was Professor Paiva PhD student at that time. Now she's a postdoc with Professor Rodrigo, who is also in this paper, now in the International Institute of Physics in Natal. So, okay, so here's our Hamiltonian. Without interactions still, and the glide plane symmetry is enforced by making these hopping terms equal. And then we just calculate the local density of states according to this prescription here. And what we get is that, okay, first we get that the local density of states is non-uniform. It depends on the coordination number of the carbon atom, because now you have these vacancies, so you have some of the atoms have coordination number 3, some 2, and this impacts the local density of states that becomes non-uniform. But the important thing is the Van Hove singularity at 0 energy, which means that there are instabilities at the Fermi level that give us space or hope that a correlated phase could develop in this material. And then we then search the weakly interacting regime of this Hamiltonian by plugging in the Coulomb interaction. So in this weakly interacting regime, we'll do a mean field calculation, as you can see here, from which we can, from this Hamiltonian, we calculate the Helmholtz free energy, and minimizing this energy, we get the magnetic order parameter, which is what you're seeing here as a function of the electron-electron interaction. And what we see is that, okay, again, it's non-uniform. But more importantly, there is a magnetization for apparently, at this point, arbitrarily weak electronic interaction, which is in contrast with pristine graphene that I have quoted before, has this critical value. And again, we have this non-uniform local magnetic moments that depends on the coordination number of the sites. And if you just plug in the whole thing on the lattice, you recognize that there will be strongly magnetized stripes, followed by weakly magnetized stripes in this fashion here. So it's a nice pattern. But let us move on to the strongly interacting regime, in which case we just use Holstein-Primakov transformation to get this Magnon Hamiltonian, which we diagonalize and then get the Magnon bands. And then we realize that the lowest Magnon band is gapless, which again points towards the spontaneous symmetry breaking for this, because of the presence of these massless Goldstone's modes, and therefore probably onset of magnetization in the system. And then we thus set ourselves to compute this magnetization, and we get that the local moments are actually, again, consistent with the weakly interacting regime, non-uniform, depending on the coordination number. So this is consistent with what we got before in the weakly interacting regime. But then if we take the average in the unit cell, we get some average local moment per unit cell, which is much smaller, not much smaller, but smaller than the one known for pristine graphene. So we get a smaller total magnetization than in pristine graphene. Now, searching the regime where interactions are of intermediate strength. So here, this we do with using quantum Monte Carlo simulations. And here you're seeing the magnetization as a function of U, and spin-spin correlation as a function of U. So the take-home message from these plots is that, again, you have a non-uniform magnetization. So at this result is very consistent. And we see a stronger spin-spin correlation at the sites which have smaller coordination number. This is seen here. As you reduce the coordination number, the spin-spin correlation becomes stronger. Okay, and if you compare with pristine graphene, you see that the correlations for when U is here, 3, so smaller than graphene's critical value, you see that the depleted or the vacancy-engineered lattice has a stronger, more pronounced correlations than in pristine graphene. So this decay here is much slower than in pristine graphene when your lattice is depleted, whereas above pristine graphene's critical point, the spin-spin correlations become almost indistinguishable this is a distance, right? As you see here. Okay, so if we now put magnetization versus U for the depleted lattice, we get this line here, okay? And we see that what this tells us is that when you vacancy engineer your lattice so that it becomes a nodal-line semimetal, you can induce magnetization at much weaker interactions than in pristine graphene, maybe even arbitrarily weak electronic interactions. And however, this magnetization saturates at a smaller value. So here is the saturated magnetization for the vacancy-engineered lattice, where the value for pristine graphene is up here. So the magnetization saturates already at a much smaller value of electronic interactions and at a lower plateau than for pristine graphene. Well, that's just that's what I said. And that's probably due to the difference in coordination numbers that you get when you vacancy engineer your lattice. Okay, so if you look at Monte Carlo results for electronic compressibility, you see that compressibility goes to 0 as U increases. That's this pattern here. So increasing U, you get this compressibility going to 0 at low temperatures, which is an indication that there is a transition to an insulating state. Okay, so your semi-metal is becoming more like an insulating, not insulating type of phase. And putting the results for magnetization in this temperature electron-electron interactions plane, the magnetic transition with the metal insulator transition, you see that they roughly coincide. So we basically are in the position to say that there is the electronic interactions actually drive a transition from a non-magnetic nodal-line semimetal at weak interactions and as you increase interactions, then the system for a certain temperature will enter this antiferromagnetic mod insulating phase, and this antiferromagnetic phase has this pattern of stripes of high and weak magnetization intercalated. And with that, I think I'm ready to come to my conclusions. So I have told you that you can engineer a two-dimensional non-symmetric material with vacancies. And with that, you gain a symmetry-enforced nodal-line semimetal. This is not actually expected to happen in 2 dimensions from basic physical grounds, because in 2 dimensions you have 1 parameter less to make the gap close. And then to get a nodal line is even more difficult. So this is per se is an interesting achievement, I would say. And then this type of nodal line semimetals, they come with a zero energy Van Hove singularity. exactly where the nodal lines which are enforced by the non-symmetric symmetry cross with accidental nodal lines. And this give opportunity for strongly correlating phenomena to arise in your material. And by exploring electronic interactions in both weakly interacting case with mean field theory and linear spin wave theory in the strong interacting regime and quantum Monte Carlo simulations for the interactions of intermediate strengths, we see that, in fact, there is a transition to insulate a non-uniform antiferromagnetic phase at very weak electron-electron interaction strengths, which is in contrast with what is known for pristine graphene that takes a much larger value of electronic interactions. And I would like to highlight that this proposal is basically relying only on symmetries. Okay, so there is no much reliance on chemical details or microscopic details of the material. So you can, in fact, engineer a robust nodal-line semimetal simply by vacancy engineering, and with electron-electron interactions that drive a transition to a correlated phase, in this case, a magnetic, non-uniform antiferromagnetic phase. So thank you very much for your attention, and I'm available for questions.
Questions here?
Thanks a lot. Very nice talk. So this, what looks to be a weak coupling instability in the system, I mean, shouldn't you be able to see that by just looking at some non-interacting susceptibility, given the band structure?
We didn't look for susceptibility.
Yeah.
Susceptibility,
yeah.
That could be a good idea, but we did spot the Van Hove singularity in the non-interacting,
right.
For the non-interacting Hamiltonian.
Yeah,
so that gives us an indication that the strongly correlated phase can develop.
Right, but I guess you should be able to know for sure if there really is a weak coupling instability, right? That is for infinitesimal coupling, whether it orders. You can see that just from a non-interacting susceptibility, I would think.
Right. I think that's a good good idea.
But you have to be careful, right? Because it's an intermediate cell order.
Right.
So you need to look at the indices.
Yeah, there's a matrix, and you have to be careful, but... Sure, yes. And sorry, if I can, one other question. So you showed what I think was experimental data just before this of these nodal lines.
No, this is DFT.
Oh, or just before this one, maybe? Was that also DFT?
Yeah, that's also DFT.
Oh, okay.
Okay.
That answers my question then. Thanks.
Mariana, this state that you find, right? It's an intra-unit cell magnetic order, right? There's no breaking of translational symmetry.
No.
No, you mean doesn't have no that
no breaking
okay.
of the of any crystallographic symmetry.
Right.
For that
so
matter.
I'm suspicious that this is actually an ultramagnetic phase, because the question is which symmetries relate. So you have, if I understood correctly, you have three different sets of sublattices, right? One that is 4, and the others are 2 and 2, right? That gives you the non-magnetic.
You mean with respect to the with respect to the coordination number?
If you look at C10, yeah, you had a picture of the magnetic order there.
Ah, okay. Sorry, that was. This one?
No, the one where you have the actual magnetic configuration with up and down spins. Yeah, that's perfect. So it looks like that you have 3 different kinds of sublattices, right? The blue, the green, and the whatever color that is. Thank you, orange.
Yeah.
It looks to me that the symmetry relating is precisely one of these non-symmetric symmetries that you have, right?
Yeah, but you would have to, this symmetry, I think you have in mind, would involve a spin flip.
That's fine, but the whole point is that it's not inversion.
No.
They're not related by inversion. So by definition, this is then an ultramagnetic phase.
Is it? Is it?
Yes.
Okay.
Wait. Rodrigo is objecting.
There is a combination of inversion and time reversal. There is one. Exchange sites 8 and 9.
No,
The center of the bond. And then we calculated the bands. They're fully degenerate at the mean field level.
Yeah, I think.
Okay, another
We
question.
had this conversation, Rodrigo and I, and well, yeah, no, that's,
I had the same question as Ilya, right? Is this really infinitesimal coupling? My intuition, I would say probably not, but it would be very interesting to find out. It's a very sharply defined question. But 2 questions on the modeling. I learned in school that carbon is 3- or 4-fold coordinate. And of course, it can be 2-fold coordinate as well, but this costs energy and some dangling electron and so forth. So in the modeling, I would have modeled this by having a change in the on-site energy at every site where I have a dangling bond. Did you do this?
yes.
Okay, good.
No.
And the second, so how do you know this number, basically?
Yeah, well, there will be a number. It's just that
Absolutely.
it's not important for the symmetry argument.
It's certainly not important, but
Yeah.
it could be very important for the actual onset of the magnetic ordering itself, right? For the size of the moment, for the variation of the moment in the unit cell and so forth. From a symmetry point of view, I would agree, but I would be surprised if it was completely irrelevant how many electrons are actually sitting on the site,
Yeah.
right? The other question was in graphene, what screens the Coulomb interaction so that I'm permitted to have a Hubbard model?
What screens?
No electrons to screen it.
Yeah.
So I would actually say, well, unless I have a gate, I would expect a 1/r Coulomb interaction.
Yeah.
So would this change the behavior?
You mean because?
Because of long-range Coulomb interactions.
Because of,
It's
okay.
not. I wouldn't think it's necessarily screened in graphene itself, right? We have some indication that there is a long-range Coulomb interaction, velocity renormalizations, and so forth, in the surgery-affected.
I'm not sure how to answer this question.
Okay, it would be interesting to see whether this matters, because the material itself, I think, has nothing that really screens its Coulomb interaction,
Yeah.
right?
So.
Just a question on materials. So are there any other ways to realize this non-symmorphic symmetry without vacancies? Like, for example, if you had a bilayer and you sort of tried to slide one layer over the other, is that another mechanism to get it, or are there issues with that approach?
I hope so, because this is the problem that I'm working on right now with bilayer and not actually twisting, because this is thermodynamically very unstable, but shifting. But we are actually trying to see if you can engineer not just nodal lines, but other nice spectral features, which are related to the symmetries with this kind of engineering of stacked material, two-dimensional materials.
Okay, one last question here.
This one last question can be split in two, and 2 comments. It'll be really quick. So, Mariana, thanks for the talk. It's really interesting. So, the first comment, yes, AB Lib lattice has an isomorph symmetry, and so concerning the degeneracy, when you show the 4 bands, so based on the fact that the lattice is isomorph, you cannot guarantee where this degeneracy happens, yes?
No.
Because it was so funny to see that when you go add 1 by 1 symmetry, this go to the high symmetry points or lines.
Yeah, because
so you can elaborate?
This is something that people typically brush under the carpet. That if you just have in this case, the glide line, and this is a two-dimensional material, so this is a detail that it's actually important. This only ensures that these bands will touch along the other direction. So in this case, along kx, but not where. And then actually you need a second symmetry to enforce, to push these 2 points to a high symmetry point, in this case, kx equals pi in the Brillouin zone.
Yeah.
But if you just have glide plane, you can actually play, if you break this inversion, it's a nice thing to do because you can move around these symmetry-enforced nodes as if they were Weyl nodes. But they're not, because they're not accidental. They will not, I think that's what you have in your mind, that you think that they could merge and split up,
No, no,
like
no.
Weyl nodes?
No, no.
Okay.
It's just talking about the degeneracy itself, because even you cannot say that it is 4 degenerate or 2 times degenerate.
Ah, no, here I can, here, for this particular type of materials, these points are 2 for degenerate.
Okay.
But
And
you don't, in general, you cannot say that.
yeah. And one last question for the electron-electron interaction part of your work. You show some results along the zigzag direction. So I didn't get it if at the end of the day you are taking a finite system, or it's in fact a infinite system.
Which
I mean,
result?
you show some results that, as you compare with the pristine graphene along zigzag direction. So it's a general question. So it's a
you mean-
finite or not? It's like a semi-infinite lattice.
No, it
It's a
depends on
nanoribbon.
which regime. If you're talking about this results in the strongly interacting regime, this is an infinite system. But for the Monte Carlo simulations, we have a finite system. So which results? This one?
Like this one.
Okay.
You just put in the label.
Yeah, here you see this is for finite system.
Okay, thanks.
Okay, have to move on. Let's thank Mariana again.
Okay.